We're now beginning our last session of the day, which is statistical modeling and sort of generally speaking. So the talks are a little bit more varied. And we're going to start with Dr. Chatterjee as our first speaker. So if you could share your slides, I'll verify that they're working and then you can get started.
Can you see the slides?
The slides are great. Your audio is coming through clearly and the recording is rolling. So please have at it. Thank you, sir.
Thank you. Thank you, organizers, for scheduling this talk. I'm sorry I cannot be present in person, but I thought this is a recent paper that we published. My co-authors and I published in Environmetrics in a special issue that was guest edited by actually some of the organizers of this conference. So thank you once again for having this on. And I thought this might be important for this community to know about, so hence this talk. So I'm Ansu Chatterjee from the University of Minnesota School of Statistics. I will be moving to University of Maryland at Baltimore County shortly, but let's get started with the talk. So here are the two co-authors for this paper, Professor Benjamin Bagozzi from the University of Delaware, and Ujjal Mukherjee. Ujjal is the person who did the most amount of work relating to the data analysis for what I'm going to present. And Ujjal is at the University of Illinois at Urbana-Champaign. And so these are the two co-authors for this work. So what are we talking about here? The work that I'm going to present links climate extremes with things that get affected with climate change. And the ones that we are targeting are political violence or conflicts between groups of human beings. That's one of the things that we'd like to see if that gets affected with climate change. And then there's a follow-up piece to this as to how does that affect, so climate change and social conflicts, how does that affect supply chains? Ujjal is a professor in the business school, so supply chains and disruptions of supply chains is pretty important for him research-wise. But it's actually pretty important to all of us because nowadays our food supply, our energy supply, so for example, we are running electronic equipments at my end and at your end, and these are run with parts that are manufactured, supplied, mined from all over the world. So how does climate change affect these things? Now, one of the reasons for us to look into this is because there's, of course, not a lot of literature relating to this, either from the climate change perspective or from the other domain sciences perspective. In particular, the social sciences literature, which is where two of the three things that we would like to link, political violence as well as how political violence might affect supply chains. So the literature relating to that is not at all clear. I mean, there are claims that, of course, there's a link. There's also claims that we don't find sufficient evidence. And both of these groups of claims are actually related to doing not high quality statistics, what I would often call very bad quality statistics. And this has been recognized by social scientists themselves. There's actually a paper in Nature about the sampling bias relating to this. So what people do when they study conflicts is that they go to a high conflict region, let's say parts of Afghanistan or Syria and places like that. And then they say that, okay, Afghanistan typically is a very hot place during summer months and there's a lot of conflict, so there must be a relation. And then some other people say, well, that's not good enough reason. And there's, of course, a lot of sampling bias, a lot of respondent-driven sampling, a lot of what's known as a streetlight effect. I mean, you zone in on a particular characteristic, and then you see everything from that particular characteristic's perspective. So that sort of a problem runs into some of the previous studies that has been going on. And many of them are pretty descriptive in nature, so not at all statistical or scientific in nature. And then this third bullet point is also very important. While sampling bias is an issue that has been highlighted in previous literature, nobody really says anything about the fact that most people, when they deal with this sort of problems, there's no notion of uncertainty quantification. I mean, people might draw a scatter plot and say, look, there seems to be a linear relationship. So pretty poor quality statistics, like I mentioned. Also, any of these kind of data, when you're looking at climate or climate change, when you're looking at political violence or things that can lead to political violence. So climate change do not have necessarily a very linear causal relationship with political violence, right? But climate change can lead to people migrating from one region to another in search for water, in search for grazing, which is what's happening in upstate Nigeria, for example, between the Hausa and the Fulani people, and a variety of things. So people do migrate, people do go to other places looking for food, for employment, and these can lead to conflicts. So there is spatio-temporal dependencies out there, and these are things that have not been accounted for in previous literature. So what we are trying to do, and what got published in this issue of environmetrics, is one framework, and I would really emphasize on the word that this is just one framework. We think it's a pretty good framework, but it's still just the start of looking at these things from a proper statistical perspective. This is not a long talk, so let me sort of just go over the broad outline of what we are dealing with here. So what kind of data do we have? We look at, of course, temperature data. That's the only climate feature that we look at. We look at temperature anomalies, so shifts from the generic trend of temperature, and I'll explain this in a minute. We have political conflict data of various types. So these have been collected from a variety of news sources using web scraping, natural language processing, and a variety of other techniques. So the political conflict data are of different types. So this could be material conflict, meaning people getting into physical clashes with each other. Also, who does what to whom kind of a thing. So people that are in conflict could be government actors. This could be policemen, this could be politicians, they can be rebel groups, they can be ordinary civilians. So there is grouping of individuals, and also conflicts could be verbal, could be material. There can be, instead of conflict, there can be cooperation. So for a particular thing, let's say there's a huge flood, an extreme climate event related occurrence probably, which can actually lead to cooperation between government agencies and rebel groups, for example. So conflicts and cooperation events of these sorts of various actors, various types of conflicts of cooperation. And then we do have data relating to exports, imports, and other things. So basically something to do with the supply chain side of things. And then what we did is the original data for these various groups are of different kinds of granularity. We aggregated these to a country and month level. So spatially, it is countrywide analysis. Temporally, it's monthly data. That's what we are looking at. And this is just to smoothen things out a bit, get rid of some idiosyncrasies in the data, and of course, this is kind of the finest granularity at which all the parts of the data exist. Okay, I'm sure you'll glaze over your eyes with this slide, and that's perfectly all right. But let me just explain this. What we have at the top level, the one that we are measuring with Y. So I is the ith country, and T is the tth month. So month being stringed out like year-month combinations. Y is the number of conflicts of some kind. Let us say material conflict between where the government is the perpetrator and civilians, so people who are neither government nor rebel groups, ordinary citizens, are the victims. Okay, so number of conflicts of that sort. These things are usually over dispersed. So all these counts are over dispersed. So we fit a negative binomial distribution with appropriate parameters. And then for the logarithm of the mean of this negative binomial, we put a Gaussian process distribution to it. A Gaussian process modeling goes to it. A Gaussian process with a mean. So the mean of this Gaussian process has an autoregressive structure. It is also dependent on, so this part, the R part, is where we stick in the climate anomaly, the temperature anomaly. And then there are other covariates. Some are time dependent and some are not time dependent. And then we have for the RT, this other parameter relating to the negative binomial, that also has a prior, well, as a distribution. And then this big long theta is all our parameters, and that gets a prior. So this is a Bayesian framework. And then here's the prior. Just to let you know, don't worry about these. The only thing that's relevant is that the gammas, and where do these gammas come from? So here, this matrix gamma is actually a diagonal matrix. There's a reason why we do this as a diagonal matrix in this paper. And these diagonal entries can be non-zero or can be zero. So we basically put a sparsity related shrinkage prior out here. This is the horseshoe prior. So the idea is some countries have a structure in their violence. So if they had incidents of conflicts in the previous month, they are likely to have it this month also. But this is not true for all the countries. This is totally incompatibility with what we see in the data. So some countries have a high level of violence, some countries have sort of a temporal dependence in the violence, but this is not universally true. Spatial dependence is captured by this kernel of the Gaussian process. So that we use a Matern kernel for the paper, but we've also reported results for other kernels. The choice of a kernel does not seem to be terribly important. So let me run this explanation list by you again, because I think this is really important. You could always read the details in the paper later. We use a negative binomial distribution because this obvious over dispersion in the data relating to the counts of conflicts. The spatial dependencies, as I mentioned, is through that Gaussian process. Basically, that kernel of the Gaussian process captures that. And we do use a Matern kernel, but we had tried out actually the first version of the paper that we submitted. We used a RBF kernel. That works just as fine. And a couple of other kernel choices also works just as fine. The mean of this Gaussian process, that has this autoregressive function as well as exogenous variables. So that's a legitimate time series. It's not observed, it's a latent time series, but it is a legitimate time series with both exogenous and endogenous factors. And because we are dealing with a very long dimensional time series, all the countries struck together as a big long vector, we use shrinkage, a Bayesian shrinkage using a horseshoe prior. Okay, let's get to the results, because as I mentioned, you can always read the paper if you want more details. How do we construct the climate anomalies? Essentially, for every country, we fix a smoother. This is, we detrend and deseasonalize the data, and then look at the difference between the observed and the red line kind of a thing. And we do three different kinds of analysis: positive anomalies, negative anomalies, and absolute values of anomalies. So, of course, positive anomalies is when you're looking at very high temperatures, and that's the one that has the most significant results. This is just a sample of 6 countries of how these things, how the temperature data looks. Just to give you a global plot, this is the temperature anomaly. This time it's just absolute values of these anomalies. Okay, so this is no longer positive and negative, but again, most of these are actually positive values. Because we're looking at So mostly countries that are warming up. Also, just to give you an idea of the response variable, and this is sort of a summarized response variable. So we looked up, for every country, we looked up the average monthly conflict count. Okay. This average is a non-negative number. This no country that has really got a zero in among the countries that we're looking at. So we looked at the logarithm of that, and that's how this figure looks. These two figures sort of look very similar to each other, which is why there's this reason why there should be a relationship between these countries. Here's one of the tables from the paper, and I think one of the more important tables. So of course, we have got a full Bayesian framework. We are using a shrinkage prior, so it's a high-dimensional Bayesian computation, and the Markov chain Monte Carlo took some work. There were some other alternative suggestions which didn't quite fulfill everything that we wanted. We just did not want only the posterior means. We wanted, of course, the full posterior distributions. So we had to do the full Markov chain Monte Carlos. And here is the case when we are looking at only positive temperature anomalies, meaning that we are looking at only heat-related, excess heat-related effects on material conflict, where people get into fights with each other. So not verbal. So basically, physical fights, murders, and things like that. What I would like you to concentrate on, of course, is this last column. So this is the probability, the posterior probability that the parameter value is less than or equal to 0. So which basically gives you an idea of whether the posterior is entirely on the left side of 0 or entirely on the right side of 0, or something like that. And you can see, if I were to do a hypothesis test, a Bayesian version of a hypothesis test, pretty much everything is significant, maybe except for ethnicity. Ethnicity shows up when we look at non-material conflicts. Ethnicity shows up in other things. But, a language division, religious division, human development index, also the signs are in the right sort. So, for example, places with high human development index have, of course, a negative value of the posterior. So the propensity for violence is lower. Temperature has a positive effect, meaning that higher temperature leads to increased conflict, and it's fairly prominently, the p-value of it up to 2 decimal places is very recognizably not far from 0. So, and if you could look at the posterior coverage, so 0.37 to 0.47, again, very, very positively skewed and so on. So this is just one of the tables from the paper. We've got several other tables and so on. And I think I should finish, hopefully staying within time. Just thank those who have partially sponsored this. So the National Science Foundation under various grants, also a grant from Cisco. And this paper appeared in Environmetrics, as I mentioned, and thanks to all of you. Thank you.
Thank you for joining us, and I'm glad your paper did make it into the special issue. It was an unusual one. Nathaniel and I did struggle to find reviewers who could handle both the Bayesian statistics and the subject matter. And I think I was responsible for that one. I think I went through 9 attempts before I got a nibble on a string. I got someone to agree to review that paper. So in the end, I'm glad we made it through, and we
thank you so much for doing
it
that.
added
it's a
something
difficult
different. It wasn't just traditional modeling, so it was very nice to include. So thank you for giving the talk. We have another session again from an online speaker. Xiaoxun, you there? I saw that you were in the Zoom earlier.
Yes, I'm here.
Yeah, perfect. Okay, hello. I'm going to make you spotlighted, and then please go ahead and share your screen.
Right, I can see the screen.
Coming through, everything's great. Please proceed.
Okay. All right. Thanks everyone for being here. And I'm currently a postdoc at the University of Wollongong, and this is a joint work with my advisors, Noor and Andrew. And also, this research is part of the Australian Research Special Initiative for Antarctica, securing Antarctica's environmental future. And it's also a collaboration with some ecologists from La Trobe University with the goal of understanding an Arctic biodiversity. So what does biodiversity mean in this context is, as opposed to the commonly used of our diversity that focuses on the number of species at single locations, here we're actually looking at beta diversity, which is usually considered as biological differences between pairs of locations. And the biological difference is usually measured using a dissimilarity index. And here's an example, the Sorensen's dissimilarity index. So it's for a pair of locations x and s prime. The dissimilarity is defined as 1 minus a similarity, which is given by 2 times the number of species common to both locations, divided by the sum of species at the 2 locations, s and s prime. So a very popular tool in ecology is called generalized dissimilarity modeling, which has been used a lot for study how beta diversity responds to environmental change or in climate change. And it's essentially a generalized linear model. So loosely speaking, we regress the dissimilarity on the changes in environment. And the linear predictor of this model is in this form. And here for each p, the absolute value of the difference of BP is the dissimilarity of the changes in environment. And our goal here is to actually look at the slope of this function BP, which correspond to the rate of changes. And here are 2 examples of the function BP. We can see that for different covariates, the shape of this function BP is different, so which indicates different rates. And you may have observed that these functions are increasing. It is not coincidence. We actually have this monotonicity assumption for BP underlying this kind of modeling, where we assume that as the environmental gradient increases or the 2 locations further apart, then the dissimilarity increases. So this model has been quite popular, but it has its limitation to account for spatial dependence. As we can see from this linear predictor, there's no element to explain the spatial dependence, or there's no spatial random effect, if you like. So when I look at this problem, I actually like to think of there are 2 spaces involved. So there's one species space where we have the species distribution data, U of S here, and then we have another space, dissimilarity space, where the index of the random variable are 2 locations. So, and the dissimilarity between 2 locations are actually functions of the species distribution, the 2 locations. As we can see from the graph here on the left, the node represents the location where we have the species distribution, and then the black line, the edge here that connect the nodes are the dissimilarity. So if we think of this similarity as a function of species distribution, and if we're happy to assume that the species distribution is spatially varying, which is usually the case, then we do need a spatial process here in this linear predictor to help us to more accurately estimate this function BP. And this problem is challenging because it's a very special spatial process. The index set here is not a single location, it is a pair of location. And another problem is that if we think of this dissimilarity as the edge of the location, then the number of edges grows quadratically with the number of locations. So our solution here is to have this class of generalized chi-square process. And our idea to building this process is to respect the connection between species space and the dissimilarity space. So this is the idea. We consider k-dimensional Gaussian process in the species space, a very simple Gaussian process, mean 0, variance 1, and the dimensions are independent of each other. And then for given a vector of positive value parameters lambda k, we define this class of generalized chi-square process such that for a pair of locations, the random variable is taken to be a weighted combination of the square distance of the Gaussian process at the two locations of interest. And it can be verified that the marginal distribution of this random variable is a generalized chi-square distribution. So, and that's why we call this process a generalized chi-square process. And the connection between the species space and the similarity space can be easily seen in the expectation. So if we take the expectation, we can see that it is a weighted combination of the variogram in the species space. So what does this mean? It means that if we believe that there, or if we observe that there are much variation in the species distribution, then we would expect that there will be large dissimilarity between locations. All right, so whenever we are looking at a spatial process, we are interested in the covariance function. And this is where things get more interesting, because in a typical geospatial problem, we're looking at covariance between two locations. But now we are looking at covariance between pairs of locations, which have actually we have 4 locations involved. And here, if you look at this formula, it's actually, it depends on the parameters lambda k and the covariance of each two of the 4 locations in the species space. And it's much more clear if we look at the graph. So remember that the nodes here are the locations, and the edges that connect the nodes are the dissimilarities. So the covariance between the 2 edges, the 2 black line here, are fully determined by the correlation, the covariance that corresponding to these red lines that connect the 4 locations. So it's very interesting that we can see here that the covariance between 2 pairs are determined by the shape and the area of this geometric object defined by the 4 locations. And the right-hand side here is a very special case where we have the 2 pairs of locations, they share a common location. All right, so when we look at covariance, we try to understand a little bit more. So we try to understand, how the covariance behave when we shift the locations or when we rotate the space. So we define homogeneous translation when the locations are shifted in the same direction, as opposed to heterogeneous translation when here the two locations can shift in different directions. So in this case, when they are shifted in the same direction, for example, horizontally, we can see that the red lines don't change at all. So what happened to the covariance? So here's what we have found. So if the Gaussian process are stationary in the species space, then we say that the process in the dissimilarity space is invariant to homogeneous translation, meaning that if we shift the locations in the same direction, the mean and the covariance won't change. And furthermore, if we assume the covariance function in the species space is isotropic, then the process in the dissimilarity space also invariant to rotation, because now we can see that even if we rotate the space, the length of these red lines doesn't change. So the process will be invariant to rotation. And then in this case, we say that it is isotropic, because both the expectation and the covariance simply depend on distances. All right, so we have developed this spatial process for dissimilarity for a pair of locations. So we're ready to write down a model for species compositional dissimilarity for biodiversity modeling. So this is our model. It is nothing but a spatial generalized linear mixed model. And the data model here is a beta distribution. And the mean of this distribution is linked to additive model, where here we have a component that can explain spatial variation. So this is the main difference between our model and the classical one in ecology, we do have a component that is able to explain spatial variation. And we also try to add more flexibility to this function BP to help us to estimate this function. So what we're going to do here is to factorize this function BP as a scale parameter times a monotonically increasing function FP that lives on the unit interval. Remember that this function BP is monotonically increasing. And we model it using a Bernstein polynomial. It is shape constrained because it has to be monotonically increasing. And this is just the form of the Bernstein polynomials, and that this is the basis function. And because we have these constraints on the shape, so we also need to we have the constraint on the Bernstein coefficients. So if we want them to be monotonically increasing, we need the coefficients to be monotonically increasing too. And the reason we're doing this, to put the Bernstein polynomials on FP, as opposed to directly putting the Bernstein polynomials on this function BP, this factorization actually allows us to incorporate prior knowledge, expert knowledge from ecologists into the shape of the function BP, which is very important in Antarctica because we have less information there from the data. Data are quite sparse. So this is what we're going to do to allow us to incorporate prior expert knowledge. We're going to first consider vector of gamma random variables with very special shape parameters. And the Bernstein coefficients are defined as the cumulative sum of the weights which are normalized gammas. And then it follows that the distribution of this vector of weights is a Dirichlet distribution, and the shape parameters of the Dirichlet are exactly the same as those in the gamma random variables. And this approach to constructing the feed, the Bernstein coefficients per se here, implies a Dirichlet process prior on the function FP with two parameters, alpha P and the baseline distribution F naught P. And that actually allows us to incorporate prior knowledge of the shape through this function F naught P. And here is a little bit simulation to help understand how this model works. So what we call this model Bernstein Dirichlet polynomials. And from left to right, when the value of the concentration parameter increase, we can see that the prior simulations are concentrating more and more around our expert knowledge. And from top to bottom, if we increase the number of M, the number of basis functions, we can see that the prior simulations are getting more and more lumpy. So this means that this parameter M controls the smoothness of the Bernstein Dirichlet polynomials. So this allows us to, based on our degree of belief on the expert knowledge, how we can elicit our bias through the values of the parameters. Okay, so a quick example of a data example. Here we are looking at Bunker Hills, which is one of the several places in Antarctica where we can look at land species diversity. And on the right-hand side here, we have the map of the Bunker Hills, a very small region, and we're specifically looking at the southern part where historically a lot of scientists have visited and collected data. And we're looking at lichens. Lichens are very important species, especially for Antarctica, because they can live in very harsh environment, and they can also support the life of other species. And the bottom right here is the temperature, the downscale temperature from reanalysis. And because the Bunker Hills are surrounded by ice, so we can see that the sides of this region are colder and the center a little bit warmer. And the other 5 panels are presence absence data of the lichens. So this actually the species distribution of the lichens. And we can see that there are more diversity if we're looking at the size of the region. But if we're looking at the center, almost every lichens exists. So we can see there are some spatial variation, in the distribution, which we might expect some dissimilarity there. So this is our result. We simply fit the model we proposed to this similarity is calculated using the Sorensen's index. And this is our inference for the function BP. We can see that the similarity change a lot when the temperature is relatively low or relatively high. And that aligns what we have examined through the spatial distribution of the lichens as well as the temperature. All right, I think this is summary. We have developed a spatial process for dissimilarities. It's a very special process because the index is a pair of locations. And then we propose a model for species compositional dissimilarity with these Bernstein D-shaped polynomials for incorporating expert knowledge. And then this is some ongoing and future work. I specifically want to highlight the first point because incorporating uncertainty from downscaling in this problem is very important because the Bunker Hills are very, very small. And for this region, we have at most 30 data points for the temperature, for example. And we're trying to downscale from 30 values to 3,000 values. So there's a lot of uncertainties going on. So we do want to incorporate uncertainty here. And I think this is it. Hopefully I do it in time. Thank you so much for listening.
Sorry, we were muted, so you didn't hear our clapping. So let's do that again for him.
Thank you.
So for time, I want to jump to the last talk, and then there will be an opportunity at the very end to speak to all three of these speakers. I just want to get the last talk of the day done, and then we've got all three of them here, and we can hopefully have a little discussion after that. So the last speaker, where are you? Edgar, are you here?
Yes,
hello, Edgar.
I'm here.
Okay, perfect.
Hello.
So I'm going to highlight you there, and please share your slides.
Okay. Here we go. Can you see it?
Yeah, that's good. We can see you, we can hear you, and we can see your slides. Please proceed.
Okay. Hi, I'm Edgar. I know that we are playing with the time, so we are very, very concrete. So I will present that work of one of my students. I'm from Mexico. We are from Tecnológico Nacional de México, Campus Sur, Guanajuato. So basically, we know that a lot of research try to investigate when the lockdown due to COVID-19, 2019. Well, there is a hypothesis that the levels of the contaminants reduce or decrease in this time. Obviously, because there are a reduction in the social minutes and the economic activities. So here in Mexico, here in Mexico, principally in Guanajuato, the lockdown was in April 2020. So we hypothesized the same thing, but with the carbon monoxide, sorry. And we made a study by if there are a decrease or what happened with these gases. So the state of Guanajuato is located in the central region of Mexico. The select of the municipalities have two important aspects that make them worth considering. First, they are part of the important industrial corridor. So this is the three municipalities, Salamanca, Irapuato, Celaya, and they're very important municipalities in Guanajuato in the economy. The second important thing or aspect was in these municipalities, they have air quality monitoring stations. So in other municipalities in another state, they don't have. So we have the information here. Celaya has one station, Irapuato and Salamanca have 2 stations. Well, what is the methodology? Well, we recollect the data information, the carbon monoxide emissions, with the data of one of the secretaries in the government of Guanajuato, the Secretary of Environment and Territorial Ordering of Guanajuato. Then the data was processed to report the particle concentration per million for each day of each month. Then we use the software R with the platform Air Studio, and we made an analysis of variance and a least significant difference test, LCD. Well, we graphic this data to see what is happening with the concentrations of the carbon monoxide between 4 years, the 2018 to 2021. And the results were this. As you can see, the levels of the carbon monoxide in the first 2 years have a lot of down. Then in the year of 2020, they increase a lot. As you can see, there is I don't know how to say this, red part in the 2020. This is the zone where the lockdown was here in Guanajuato. So we can see there is a decrease, at least in this station in Celaya, from these levels of carbon monoxide, as you can see. Then when we this the variance analysis and the LCD test, as you can see, the levels are similar in the first 2 years. The last 2 years are higher. So, and as you can see, the treatments with the same level are not significantly different. So the groups of BB are basically statistical the same as the first 2 years, and the last 2 years. The results basically are the same in the next monitor stations. So in Irapuato, station 1 or station A, you can see that in the lockdown also there is a decrease in the lockdown, and this is the variance analysis. So the same thing, the first 2 years have the same levels of carbon monoxide, and the next 2 years the same increase, as you can see, 3 and 4 times the levels. Then if we have the Irapuato B, the next station, and this is a different results, because as you can see in the last 2 years, the levels increase and maintain, but in the lockdown increase a little. So when you can see the results of the LC test, well, of course, the similar thing that the other stations. So basically, the 2 last years have the same levels of carbon monoxide. And there's a little bit significant difference between the year 28 and 2019. Then we have the Salamanca, the first station, and in the lockdown, basically the data, the levels of carbon monoxide are the same, statistical. And the LCD results shows that all years have a different average in the levels, but basically the same on the other stations. The last 2 years have increased the levels of carbon monoxide. And the last station, Salamanca B, also, well, in the lockdown, there is an increase of the levels. And when see the results of the LCD, basically, well, the year 2018, we only have data of 1 month, December, and this is the result that we have obtained. But as the other studies and the other monitor stations, the last 2 years have the levels increase in the carbon monoxide. But in the last year, decreased a little. But in this particular station, as you can see, the average in the year 2020 is the biggest in the other stations. So, well, this is only the graphic of the results that the data we have collected and analyzed. We understand that if this data is not measured correctly, well, we know we can make the next conclusion. So we hope that these results are measured correctly. As conclusions, we can conclude that the carbon monoxide levels in Celaya and Irapuato decrease in the lockdown. So we can assume that in the other municipalities, the lockdown measures were not followed, or there were permanent carbon monoxide emission. I don't know, maybe. It is necessary to conduct a study of the carbon monoxide emissions during the day and the night to review social activity. All the data is by hour in each day and then in each month. So we can analyze that if the people make the lockdown measures correctly by analysis the data in the night in the day. So this is the we can measure in the years of in the 2020 and the 2021, there was an increase in the carbon monoxide emissions in all stations. So this is what we have a precaution with the data, because in the other stations, in the same year, the levels increase. And I'm afraid that in these years, in the last year, is the same. We need to review the data, the station are collected. The increase of these carbon monoxide emissions was up to 5 times higher on average than the 2018 and 2019. And for last, in the station Irapuato B, or second station, report higher levels of carbon monoxide values in every month of the last 2 years that were 2020 and 2021. So we know there are a lot of variables that they can conduct to these results. So we are measured the wind speed and the direction, because this data we can gain us a clue where they come from, these emissions. So that's all.
Sorry, you need to clap again. It was muted again. Hi, Edgar. Sorry, Wesley had to pop out in case you're wondering why I've changed. Thank you very much for your presentation. Really interesting. So we'll pass back now to all speakers and we can take questions for any speakers in this session. Edgar, could you, oh, fab, thank you. So we have a question at the front, thank you.
Raoul Bonson from Trent University. I have a question for Mr. Shane. First of all, congratulate you for very novel approach to trying to reconcile biodiversity with geostatistics or geostatistical theory. My main question there is that your spatial dependent dissimilarity, does it follow any of the premises of a regionalized variable theory, such as the hypothesis of stationarity? Did you compare that your biodiversity, your dissimilarity measures, whether they have or they follow any of the tenets of stationarity hypothesis? In your statistics, is based on the hypothesis of stationarity, and therefore the semi-variables that are derived, some of them are compliant with the stationarity. Your models today, did you compare them, or did you observe whether they follow the traditional statistical hypothesis of the stationarity?
Okay, sorry, I'm trying to understand the question. So, do you mean the stationarity in the turnover function BP, as opposed?
Yeah.
Yes. So I thought about that before. Definitely. So I think this function is rather species specific. Like for lichens, there's a specific function BP, and then for mosses or for birds, there should be a very specific function that attached to that species, and but of course, for different species, if they are living in different regions, this function may be modified a little bit because of the environment surrounded, because of the climate. But in general, I think it is okay to for this basic model to assume stationarity in the function, in the turnover function BP. But I think to have to allow the model to be more flexible in order to allow the model to pick up some non-stationarity in this function BP, I think this is a future step to try to adapt this kind of, for example, regional effects in this respondents of the biodiversity to climate change.
Thank you very much, Xiao-Chan. Abdul.
Yeah, I thought that what you have is invariance on the shape. When you move your rectangular or whatever it is, then you show that the distance is preserved. And this, what you said, is giving you the stationarity. See, when you have the four corners and you move the graph, then you have invariance. The shape is invariant.
Sorry, I couldn't hear the question clearly. Could the host repeat the question?
Well, I was commenting on the stationarity. I was commenting on the stationarity. Stationarity as a result of the invariance. In invariance, it's okay. It's okay. So I have with another quick point that for the same thing.
Okay.
It's okay. No, I think
Do you refer to these slides?
I was saying, you are moving the rectangular or whatever it is you call it, and it is invariance. The distance is invariant because it is diagonal.
Might have to move closer to the microphone.
I think in your previous slide, Xiaoqian.
The stationarity is connected with the invariance. And the invariance, because the distances that you have when you are moving, the shape doesn't change. You move it, doesn't change. It's really a generalization of non-stationarity, of stationarity in the usual variogram situation, but it's in the shape. It's okay. It's okay. It's okay. I think it's okay. You see, do you see what it is? The shape. It's just the shape is invariant.
Yeah.
And this is what his definition of stationarity is. But the question that it's okay.
Can you hear Xiaoqian?
Yeah, a little bit. I caught the words of the stationarity and the shape, and yeah, I thought a lot about, you know, how the shape would change or not change depending on like on this like if we how do we move this low, for like how does the shape depends on how we move these pairs of locations. And I think in terms of homogeneous translation, the shape would then change if all of the 4 locations are shifted in the same way. Yeah.
Yeah, that's what you defined as stationary. But the question, can you hear me?
Yes.
Are you estimating the linear combinations of the chi-squared? These lambda 1, lambda 2, whatever it is, the lambdas. Are
Yes.
you estimating these to get the combination of the distance?
I fit a Gaussian process model for this, right? And I'm estimating the parameters of the covariance functions, and then this lambda case jointly.
Because I don't know what the lambdas are, because I thought it should be a monotonic declining function as the distance increase. Should be. It's okay.
It's fine. Declining.
Yeah, sorry, I couldn't hear very clearly. I'm sorry.
So the final point was, are the lambdas monotonically decreasing as the distance increases?
Oh, the lambdas. No, I don't think we put constraints on lambdas. No, another way to think of lambdas is the variance of the Gaussian processes. So we could actually put the lambdas, we can squeeze them in into this CK. So we can but we decided to write it in this way to indicate the contribution of each mixture component here to the dissimilarity. But no, we don't have any like assumptions on this lambda k. It is just positive.
Okay, thank you so much, Xiao Chan. Any other questions for the other speakers? Yeah.
Just a general comment,
Mhm.
if I may. I think it's very important. I think we're we're in a transition period where we're moving from the geostatistical realm of looking at spatial data. And very likely when we have enough cases of a certain species of a certain certain problem, we're moving very rapidly into the territory of that we may not want to move, the AI.
Mhm.
So very likely, instead of having to model these things, we can throw a large stack of data to an AI algorithm. Then the AI could be able to provide us with the semi-variogram or the special variability function, and then we'll be able to predict. We are not there yet, but if I might just say, I don't see that it would be too long before somebody could come out with a strategy that instead of the complex statistical analysis, they throw a bundle of data, large data, and get an algorithm to learn it and make those projections or predictions of what we have now as a chi-square process, especially similarity over any semi-variogram of any other kind.
But we just need to be able to trust it, right? And have the uncertainty as well.
Exactly what research would come into.
Yeah.
So.
Yeah, great point. Thank you. Any other questions or comments for the speakers?
Well, I think the linear combination of chi-square can be approximated very well with ordinary chi-square distribution. All what you have to do is to take the expected values and the degrees of freedom. So what he has is the distance is the chi-square with 1 degree of freedom. So you have this series of exponential distribution if you think about it, and then you can have a good approximation. I just didn't get the beta component of the analysis itself, because he moved from the chi-square into the beta and the F distribution. And one has to read the article
to get all the details. Sure. Thank you very much, Abdul. So if there's no other questions or comments in the room or online, I would just like to thank our 3 speakers again. Thank you very much. For those online, that's the end of our second day. Thank you very much for joining us. And Wesley has sent an email about the session tomorrow morning. There's just a session tomorrow morning for those online. For those in the room, there's also a session online in the room, and then there's the excursion tomorrow afternoon. And again, all the details are in Wesley's email. So thank you very much, everybody, for coming today.
Cool.